Hi, everyone. This lecture is about atoms, and it's leading up to talking about molecules. And molecules are made of atoms. It's very important to understand this. I know this is chemistry, but in order to understand living systems, you must understand the chemistry that's going on in those living systems. And you must know something about the atom and the subatomic particles that make up that atom. So for a lot of you, this is going to be a pretty boring lecture, but it becomes really important in understanding those really interesting chemical processes that we're going to talk about later in the semester. You've probably all seen this periodic table of elements before on a classroom wall, in a textbook, or when you took chemistry, you had to actually use it. We're going to talk about it a little bit today. Elements are what all matter in the universe is made up of. So whether it's your car, the chair you're sitting in, the plant in your yard, those are all made up of these elements. And the smallest unit of that element that still retains all the chemical properties of that element is what's called an atom. So I'm going to start just by writing a few definitions for you. So matter is a really important one. It's anything in the universe that has mass and occupies space. That's pretty much everything, right? But it's not energy. Energy doesn't have mass. So there are things in the universe that are not matter. But for this class, we're going to mostly start by talking about matter. We'll talk about energy in a future unit. And all matter is made up of atoms. You can also, another term for this is comprised of atoms. And again, an atom is the smallest unit that you can break those elements down to, and it still retains the chemical properties of that element. Anything smaller than that is going to be what we call subatomic particles, and we're going to talk about those today too. So an atom is the smallest unit that retains or keeps all the chemical properties of that element. And it's important to understand the structure of the atom and the role that each of those major three subatomic particles play in the structure of that atom, and how that affects which atoms bond with which to make molecules. That's going to be a really important part of the story. So that's why it's important to know something about subatomic particles. There are more than 3 types of subatomic particles, but in this class, we're going to talk about 3 different types of subatomic particles. And these are the particles that make up the atom. So if you broke it down to smaller than the atom, you're looking at subatomic particles. Those are going to be what we call protons, neutrons, and electrons. Those are the 3 we're going to talk about today. If you look at the basic structure of any atom, they all have the same general arrangement. And that is that there's this region in the center called the nucleus of the atom. So just as your cells have a nucleus, every atom has this region in the center called the nucleus. It's not an actual structure, it's more of a region. In that nucleus are 2 of these 3 subatomic particles. The protons, which we're going to represent with the letter P, and the neutrons, which we'll represent with the letter N. So here in the nucleus are protons and neutrons. Then orbiting outside that nucleus, around the nucleus with some major distance between the nucleus and where this is happening, so orbiting way out here somewhere, are the electrons, which we'll represent with a little green E. The number of protons, neutrons, and electrons differs for each atom. And in particular, the number of protons that an atom has is going to determine what elements you're looking at. So if we go back to that periodic table, every element on that periodic table has a different number of protons and in the nucleus, and that's what's going to define that element. If you look at this periodic table, you can see hydrogen. I know this is really hard to see. It's really small. Anything you absolutely need to know from here, I'm going to draw it bigger for you, so don't worry about that. Hydrogen is the first element on the periodic table, and it has a little 1 right here. Helium is number 2. Lithium is number 3. Beryllium number 4, and it just keeps going in order. That number is called the atomic number of the element. And that atomic number actually represents the number of protons that each atom has in its nucleus. And so let's write that down. The atomic number equals the number of protons in the nucleus of that atom. And everything on the periodic table is arranged in order of atomic number. So hydrogen is the first element on the periodic table, and it has an atomic number of 1. That means that hydrogen has 1 proton in its nucleus. Helium is atomic number 2. That means that helium has 2 protons in the nucleus. Carbon, atomic number 6, 6 protons in the nucleus, and so on. So every element on that periodic table is arranged by atomic number, and that atomic number represents the number of protons that are in the nucleus of that atom. That atomic number also represents the number of electrons, because for every neutral atom on that periodic table, the number of protons equals the number of electrons. That means for every element on the periodic table in its neutral state, that atomic number equals the number of protons. It also equals the number of electrons. It's not protons plus electrons, it's the number of each, because those are equal. In what we call a neutral atom, which is how all the atoms exist on the periodic table, the number of protons equals the number of electrons. Why do we call this neutral? Neutral has something to do in this case with electrical charge, because 2 of those 3 subatomic particles that I just told you about actually have a net electrical charge. And that is really, really important to understand. So let's go back and look at that for a second. Looking at the nucleus here, protons always have a positive electrical charge. So that means in the nucleus, these protons are positively charged. The electrons are actually negatively charged. And the neutrons, neutral, actually have no charge. So what that means, if you look at the nucleus has positively charged particles, and it has particles with no charge. That means the nucleus really has a net positive charge. While orbiting outside the nucleus are these negatively charged electrons. If the number of positively charged particles equals the number of negatively charged, then that means it's neutral. There is no net charge. Let's look at what I mean by that. So going back to these elements, let's use carbon as our example. Carbon is atomic number 6. So that means that carbon has 6 protons, and it also has 6 electrons. In other words, it has 6 positive subatomic particles, and it has 6 negatively charged subatomic particles. And that means it has 0 net charge. It's a neutral atom, no net electrical charge. Those balance each other. Not only do they balance each other, but something you might know about electrical charge is that opposite charges attract. In other words, positive and negative are attracted to each other. So that means those electrons that are orbiting outside the nucleus, those are attracted to those positively charged protons. And that's actually what holds that atom together. That atom is being held together because those electrons orbiting outside the nucleus are attracted to the protons that are in the nucleus. Now, this distance is really pretty great between the two, but yet that attraction is still there. They're never going to get pulled in. There's going to be some space in between there because those electrons are moving so quickly that they never actually get pulled into the nucleus, but it's holding that atom together. So this is called electrical force. And it really holds together the atom. And if it's holding together the atom and all matter in the universe is comprised of atoms, it really holds together all matter in the universe. So that's a pretty important concept. When we look at the neutrons, they have no net charge in the nucleus. So that's why the nucleus has a net positive charge. So to really understand the role of those neutrons, you might think, well, they have no charge. What are they doing? Why are they even there? In order to understand that, we need to really look at a model of an atom that really has more than one proton and more than one electron and more than one neutron. So let's look at the periodic table again. Sorry, I'm scrolling the wrong way here. Let's look at, well, let's look at carbon. I'm going to use carbon as our example. So I'm going to draw carbon just exactly as it appears there on the periodic table. Again, I'm really sorry I can't show you the big periodic table here on the screen and then right on that. It's just not really possible with this format I've got right here. So if you look at that square or a little rectangle, I guess it is, on the periodic table, a couple of things that are important. C is the chemical symbol for carbon. And every element on that periodic table has a chemical symbol that represents it. Sometimes it's the first letter of that element. Sometimes it's the first 1 or 2 letters of the Latin or Greek name for that element. It really varies. There are going to be some that you should learn for this class, and those are the ones that make up living organisms. And we'll get to that when we talk about molecules. So see, this is the chemical symbol for carbon. And if you look at a periodic table, you'll see 2 additional numbers. One is up here in the left, it's a 6, and down here you'll see a 12. This is, again, the atomic number. And remember that atomic number is the number of protons, and it's also the number of electrons that orbit outside the nucleus of that atom. And then this number here is called the atomic mass. And on Earth, that is equal to the atomic weight. In other words, that is how much one atom of carbon weighs, 12. Okay, what are the units? It's not grams. 12 grams is pretty heavy. It's something called atomic mass units or Daltons. So the units for atomic mass are most commonly abbreviated AMU, which stands for atomic mass units. You'll also sometimes see it written as Daltons. And there is a specific mass associated with that. If you're curious what it is, one atomic mass unit is 1.67 times 10 to the minus 24 grams. So that is a very, very, very small mass. It just so happens that one proton weighs one atomic mass unit. I'm going to make my ones a little differently so they don't look like L's. And one neutron weighs one atomic mass unit. Sorry, that's really messy the way I wrote that. Electrons are so small that their weight does not really matter in this story. Electrons actually weigh 0.000549 atomic mass units. This atomic mass is really made up of the protons and the neutrons. The electrons don't really contribute significantly. Think of it this way. If you got on the scale to find out your weight, you might take your clothes off, your heavy shoes, but you're not going to take off your ring, right? Because it doesn't really contribute significantly to your weight. Unless you Kim Kardashian or something and have this ginormous diamond, maybe then it would, but even then it probably still wouldn't. So the electrons don't really contribute to the mass of an atom, but the protons and neutrons do. So let's look at this. Carbon weighs 12, and that atomic mass equals the protons plus the neutrons. And since they each weigh 1, it actually equals the number of protons and the number of neutrons added together. So atomic mass equals number of protons plus the number of neutrons. So that 12 is telling us that we actually have 12 protons and neutrons combined. We know we have 6 protons, so that means we must have 6 neutrons in carbon also. Let's draw that out. Sorry, I have a cold and I keep pausing the video because I keep having to go cough. So sometimes I'll just cough without pausing, and sometimes if it's really bad, I'll pause and go cough off screen. So I'm really sorry about that. Let's draw this figure. So carbon, atomic number 6, atomic mass of 12, and that 12 equals the number of protons plus the number of neutrons. We know that carbon has 6 protons. So that means that 12 equals number of protons, which is 6, plus the number of neutrons. So to get the number of neutrons, all we have to do is subtract 6 from each side. That means that carbon has 6 neutrons. So that 12 is 6 protons plus 6 neutrons. Why is it the number? It's because they each weigh 1. So if we did, it would be 6 times 1 Dalton plus 6 times 1 Dalton. And anything times 1 is its own number. So let's look at something where they're not equal. Let's look at another element on the periodic table. Let's scroll up here. Oops, gosh, that got really small. Let's look at something where they're not equal. Let's look at fluorine. It's atomic number 9 and it weighs 19. So scrolling back down. Fluorine, represented by the letter F. If we go back up there again and look at it, it's atomic number 9. Sorry, it's really hard to see here. It's atomic number 9, and its atomic mass is 19. So 9 and 19. Okay, how many protons does fluorine have in the nucleus? It has 9 because that's the atomic number. So this represents the number of protons in the nucleus of fluorine. This is the atomic mass, and that is equal to the number of protons plus the number of neutrons. And we know the number of protons is 9. So to get the number of neutrons, we just have to subtract 19 minus 9 is 10. That means there are 10 neutrons in the nucleus of fluorine. Protons and neutrons are not equal in an atom. Sometimes they are, but they don't have to be. Protons and electrons do have to be equal. So in other words, fluorine has 9 protons. It also has 9 electrons. If we looked at the nucleus of fluorine, let's draw it. So here's our nucleus of fluorine. You would have 9 positively charged subatomic particles, in other words, 9 protons in the nucleus. And orbiting out here, you'd have 9 negatively charged particles. And then we know we have 10 neutrons. So that means in the nucleus, there are going to be 10 neutrons. Okay, so this would be our 9 protons, and this would be our 9 electrons. In other words, fluorine is made up of 9 positively charged subatomic particles, 9 negatively charged, and 10 with no charge. If the positives equal the negatives, this is balanced, that's neutral, there's no net electrical charge. Those electrons and those protons are opposite charge, negative and positive. So they're attracted to each other. And that's what's holding that atom together. Now we get to the role of the neutrons, finally in this story. Opposite charges attract each other. Like charges repel each other. If you've ever played with magnets as a kid, if you turn magnets one way, they'll attract each other. If you turn them the other way, they'll repel each other. You can't push them together. No matter what you do, you feel that force. So same charges repel each other. So in other words, positive and positive repel each other, and negative repel each other. So here we have a nucleus with all these positively charged particles. Looking at fluorine, there's 9 positively charged particles that are all trying to repel each other. The only thing that keeps that nucleus together and causes it to not just disintegrate are those neutrons. Those neutrons separate the protons and keep them from repelling each other. They're kind of standing in between them, like, nope, you two, knock it off. And that's what holds that nucleus together. And you don't need to know this term. It's called nuclear force, but that's actually what holds the nucleus of the atom together. It's one of the forces in physics. So opposite charges attract. that electrical force that holds the atom together and therefore holds together all matter in the universe. And then nuclear force is what's holding that nucleus together. And that's the role of the neutrons, keeping those protons separate from each other so they don't repel each other. Okay, let's look at a couple of other elements on the periodic table just for practice. So let's look at lithium. If we scroll up, you see Li is the abbreviation for lithium, and it's right here. It's atomic number 3, and it has an atomic mass of 7. Okay, so let's go back down. Sorry about this. Okay, 3 and 7. That means that lithium has how many protons in the nucleus? 3. That's what that atomic number represents. How many electrons does it have? Also 3. So lithium has 3 protons. It has 3 electrons, therefore no net charge. How about neutrons? How many neutrons does lithium have? That's where this 7 comes into play. Remember, this is the atomic mass, and that equals the number of protons plus the number of neutrons. If we know we have 3 protons, then how many neutrons must we have? It's going to be 7 minus 3, which is 4. So 4 plus 3 is what makes up that 7. So again, this is the atomic mass. And that atomic mass is made up of the number of protons plus the number of neutrons. So for the test in this class, you should be able to look at an element and you should be able to tell me what that 3 represents. You should be able to tell me the number of electrons that element has, the number of protons it has, and the number of neutrons it has. So for every element on the periodic table, you should be able to tell the number of protons, the number of neutrons, and the number of electrons. And it's really important to know that the number of protons equals the number of electrons. In other words, the number of positively charged particles equals the number of negatively charged particles in a neutral atom on the periodic table. That is really, really important. What we're going to talk about in the next lecture is arrangement of electrons. And that's going to be hugely important in understanding the chemical behavior of an element. And how that atom behaves is going to determine who bonds with whom to form molecules. I think it's really important not to memorize the periodic table, but understand how to use it. And on the exam, you'll be allowed to use the periodic table, and you'll be asked some questions from the periodic table, but you'll never have to memorize it. And in the next lecture, when we talk about how the electrons are arranged through what we're going to call electron configuration, you're going to understand a little bit more about why it's so important to understand these subatomic particles. Okay, that's all for this one. And the next lecture, we're going to start with electron configuration.